Hello, welcome everybody. My name is Just Herder. I am head of department of the Department of Precision and Microsystems Engineering. And great, thank you for joining this meeting. We as a department design precision machines from very large down to the nanoscale. And we proudly also provide the master tracks of high-tech engineering and Opto-Mechatronics. So our mission is to prepare you for a career as a science-based engineer in the fields of high-tech engineering, health and microsystems technology. So here you can see a couple of machines that are very big as a whole, but are based on very precise working principles. And these are very important for the Dutch economy. We are very strong in high-tech engineering, and we serve many companies globally with this technology. And therefore alone, it is already scientifically relevant, societally relevant. But also we see a trend towards more sustainable technologies using less energy, less materials. And also we see a broadening of applications from high-tech engineering all the way to health and microsystems. So sometimes without knowing, all of us use a lot of the results and the products that are created by these machines. All right, so there is an urge to create machines and systems that are faster, more accurate and precise, stronger, lighter, and as I mentioned also using less energy, less material, and are easier to recycle, and all of those important things. Now, in order to do that, we need a thorough understanding of their basic functioning, and also knowledge about materials and new materials that we need for those techniques, as well as their production and the manufacturing concepts, metrology, modeling, design tools, and more and more we can see integration of multifunctionality. In classical mechanical engineering, we build a machine by assembling it from parts that have highly specialized functionality. So we put them together in a high-tech machine. But more and more we create structures that have a lot of functionality already integrated in the bulk material. So that if we can create parts out of those, they have the functionality already integrated. So in order to master all this, we propose a program based on engineering and physics and other disciplines, and blend them together in a program that is resulting in this idea of science-based engineering and design. All right, Ron will take over here and go into the details of this curriculum.
Yes, thanks, Just. So, science-based engineering, and the courses that we provide are reflecting that basic ideas. So, targeting high-tech systems, health, and scientific instrumentation, with this special emphasis on precision and miniaturization in mechanical engineering. And we do that in different focus areas. Within our group, we have different subgroups, if you like, that are considering different topics, different focus areas. We have the basic fundamental mechanical engineering courses, groups, engineering mechanics, engineering dynamics. And then for the design, we have the mechatronics system design and Opto-Mechatronics. And the micro-nano engineering is the group that is specifically looking at the small scale topics. So what kind of keywords can you imagine with these focus areas? Well, for engineering mechanics, we have computational mechanics, optimization, which is a strong point, and mechanical design. Dynamics, system dynamics, numerical and experimental, and nonlinear. These are the keywords that are important in our group. The mechatronic system design, there we are looking at the system as a whole, and as it is constructed out of sensors, the combination of sensors, actuators, mechanisms, and control. Micro nano engineering, we're looking at the fabrication techniques that are possible to realize, to materialize these small scale devices, but also the design and the tools and instrumentation that are needed to get there. Finally, the Opto-Mechatronics group, we are specifically looking at the optical systems, the high resolution, high accuracy optical systems that are being developed, and the control, and in particular also the design aspects that are important there. And so these are the different focus areas, and our courses reflect this. So what you see here in this slide is an overview of your first master year. So basically we see 4 columns: Q1, Q2, Q3, I hope my mouse is visible, and Q4. And within each quarter we have 15 EC, 15 credits that you have to fill. So as you can see, we have in Q1, Q2, 2 gray boxes: physics for mechanical engineers and nonlinear mechanics. These are courses that are part of the set of obligatory courses for all mechanical engineering master students. Also in Q3 we have measurement technology. Then in addition to these courses, we have our own courses that we think are most relevant for our track, and these are the courses in blue. You can see 7 courses here in blue. You're requested to choose at least 5 out of these 7 courses for your program. So Q1, engineering dynamics, optics, mechatronic system design in Q2, and continuing in Q3 and Q4 with precision mechanism design, fundamentals of mechanical analysis, micro and nano systems, and optimization. And then finally, dark gray, there is also this social course. One social course is required in your program at least. So these are compulsory courses. You can choose, like I said, 5 out of 7. And in addition, the remaining EC you can fill with recommended courses and free electives. And so here there are some recommended electives. We won't go into those electives today, or unless you request. And then there is still space remaining in the program. There's still a lot more possible. And there you can use free electives out of all relevant courses within the university or even outside university. So you can look for courses at aerospace, for instance, or civil engineering, or even in one of the other universities in Leiden, Erasmus are also possible. So the courses, very short. Engineering dynamics, there you will see basically you will continue the dynamics from bachelor, but in this case, the keywords are linear vibration, stability, and dynamic modeling. These are the things that are very specifically targeted in this course. Optics, the basics of optics. So we are mechanical engineers working in a field of physicists looking into optics. You need to learn how to talk to physicists on this topic, and of course understand the basics. And this is what you will learn in this course. Mechatronic system design is the course continuing mechatronics from bachelor, and here you will learn how to look at the design of a mechatronic system as the collection of the different parts, not only the design of the system itself, but also the sensors and actuators needed to drive that system, and the control that is used to position the stage or the device that you're trying to control. Precision mechanism design, again, a design-oriented course split in 2 quarters. In quarter 3, you will be looking at the theory and of how to design precision mechanisms. So what are the rules, the guidelines that you can use to come up with a better mechanism or a better system? So look very specifically at the degrees of freedom that you are looking to constrain or not to constrain. How to get the stiffness that you like. Use flexures or compliance to get rid of just hinges or bearings in your system and replace them with compliant design. Look at errors that can be introduced in your design through hysteresis or microslip. And finally, also look at static and dynamic balancing. In quarter 4, you will continue with a group project where from an assignment from a company involved, the groups will work on the development of a very specific design, valuable and relevant for that company. A very interesting part of this course. Fundamental of mechanical analysis, again, back to the fundamentals of mechanical engineering. What are the laws that govern the systems that we are looking at, and how do you model these, and how do you incorporate that into your design? Also, micro and nano systems. So large part of our group is looking into micro and nano systems. And on this photograph, you see a micro gripper. So a very small device, as you can see here on the scale, where 2 prongs are being brought together by expanding heat, by expanding beams due to heat, which is pushing against this arm and then therefore pushing this gripper. And you will learn how to design this kind of device, how to realize it, how to materialize it. And in this slide, you can see the designs that different student groups came up with to again develop this micro gripper. Finally, the engineering optimization course is a course where you will learn how to use optimization, as the title says. We have looked at designing systems, and then the question that we always have is this the best system that we can build, or is it possible to build a better one? Optimization, topology optimization, or mathematical numerical optimization is a tool that you can use to find a better design, starting with an initial design. And in this course, you will learn the mathematical tools that you need to accomplish this. So these are the courses that we've looked at, these blue courses. And then in the green, there are the additional courses, the recommended electives, and then not listed on this sheet are the free electives. There are way too many free electives to list here on the screen. It is important to realize that although these 2 slides seem to be filled, there is still sufficient freedom, ample freedom even to choose free electives, to look at courses in other departments, other faculties, or other universities, nationally or internationally, where there are topics that are of interest to you and that might contribute to your education here at HTE or OM. So at the end of your first year, it's time to start looking for the topic for the second year. Our second year is a year that preferably is filled with a research project that is completely filled. So one research project for the full year. That is in contrast with some other groups where you have different topics that you are looking at in the final year. So we need to go deep. We need to have sufficient time to go into detail in the topics that we're looking at. So we'll start with a literature survey and project proposal on that topic that you are going to look for. Project proposal here is important. At the end of the first couple of months, you will define together with your supervisor the topic that you will continue on. So it's not, you don't start with a fully fixed assignment. This assignment is developed by you and together with your supervisor through your study of the literature that is available in a certain topic. You will determine what is the gap in knowledge here and what is of interest for us and for society to be developed. Then after that, you will start with your project. And the first part, after the first part, there will be a midterm evaluation. Are we progressing nicely to where we want to go? And then finally, the latter half of your second year is you're working on your thesis. Finalizing your thesis in a report, preferably with a scientific paper that is part of that report. Here you can see also internship. It is possible to do an industrial internship. However, we do not prefer to have this industrial internship in the second year because, well, it takes away from the time we have to go deep in the topics that we are interested in. What are these thesis topics? Well, you can start with looking at all the research that is being done within the department. So go to any member of the staff that you think is doing interesting work and talk to them. It can be any subject within the full department. It doesn't have to be, it's not limited to just the focus area that you have selected the courses for. Like I said, it's related to the research of the staff and the PhDs involved there. We also have industry, companies that are working together with us to develop the research, and many of them have interesting positions for a final project. And it is also possible to find or suggest a topic yourself, of course, within the scope of high-tech engineering or Opto-Mechatronics, but if you think, well, I'm really interested in this and this topic, please suggest it to the staff member that is most closely related to that topic. And you will find out who the staff member is during the course of your first year already. So then after graduation, we have this whole list of companies that, and more, of course, this is a very small subset of companies that we have contact with and that are working together with us. And we can see different companies, smaller startup companies to huge international companies to research organizations. Our students, our graduates will end up in all types of industry and all types of positions. So high-tech industry, research institutes, working at companies that perhaps seem to be slightly outside the focus of HTE, but have very much use for the graduates that we produce in design and optimization, or in metrology, or in microsystems application. So even outside the typical high-tech industry, all our students find a nice position. And of course, because we are working from science-based engineering, we are looking at the fundamentals, and the fundamentals can be applied anywhere. Don't forget that we are working on science-based engineering. So a lot of our development comes from research. So we always have interest in to talk to students who might be interested in following up in a PhD position. We do not have a guaranteed position. We do not have many PhD positions, but we do have positions. And if you're really interested to continue in research and development, or interested in an academic career, then please talk to us fairly soon in your first year and indicate that you might be interested in doing this. So we can work together to see if it's possible to realize. So for more information about this event or any questions about our education, contact me on the right, or Evelien Matroos, who is also present in the chat. She has probably announced herself by now. And we are always available for questions and for more information. Also, if you want to chat to our master students, which I can fully imagine that you would prefer to, instead of just talking to staff, there will be an online event next week, and you can register via the link listed here on the slide. And well, our student association, Dispute Taylor, is there. They are very active. They are there to support their fellow students. They are organizing social events. They are working together with the staff to improve education. And all in all, a important part of the community that is high-tech engineering and Opto-Mechatronics. And just to give you an overview of the possibilities for your second year, I would like to give the word back to Just and go through some of our master projects.
Okay, thanks, Ron. Thanks for this overview of the first year curriculum. And I hope you agree that this is a very solid program that will prepare you for pretty much any career, but especially for high-tech industry and health. In the next part of this presentation, we will show you some of the projects that were done by master students. And we will show that they range from very large systems with high precision features all the way to small systems. And in all cases, precision is one of the key factors. Also, you will see that there are design-oriented projects, more analysis-based projects, or various nature of these projects. Just before we start, one more comment. In the beginning of the first year master, we will help you select a set of courses, so a curriculum that matches your expectations and your career vision. By the end of that year, there is also a market with master projects that help you select the direction for your graduation projects. Okay, so let's go ahead and show some impressions of projects that have been going on recently. So this is the graphical summary, and you can see a lot of machines at different scales, from very large to very small, like here in the top. And you can see a range of application fields, from high-tech industry to biomedical applications and microsystems. So this is a project where function integration of various functions into a material structure was the target. In this case, it is a project of printing a structure, also known as a metamaterial structure, where the bulk gains their properties not only from the material of which it is made, but also of the microstructure of which it is built. And in particular, we are now working towards active metamaterials that do not only have passive, let's say, remarkable properties, but that can also be actuated to perform certain activities or certain functions. This is a project about handling of delicate substrates like wafers or solar cells that need to produce more with less material and therefore become more brittle. And handling these delicate structures is a challenge. So the idea is to handle them without touching them at all by putting them on an air layer. And by not only generating pressure but also flow, we can also manipulate these structures and do precise positioning. It's one of these projects where we show that things can be done differently, and that is one of the drivers of much of our research. Here you can see a biomedical application where we investigate how tissue responds to mechanical environments. In particular, we try to help cells decide on how to specialize by providing the proper environment. And by doing so, we want to understand the biomedical mechanisms underlying certain diseases. Here an example of big machines that are governed by tiny details. This is a bearing system for wind turbines, where the idea is to create bearings that are adaptive to shape changes, because the bearings in these systems are very big, and even though they may seem massive and solid, they will deform. And to accommodate these deformations, we create bearings based on thin films that are adaptable to their shape. This is a project from dynamics at small scale, where magnetic levitation is applied to create all kinds of principles that can be used, for instance, as a weighing scale of tiny droplets in this case, of oscillators, and even of micromotors. So this is still at millimeter scale, I would say, but the technology has the potential to be further miniaturized. Here you can see a project with multiple applications. It is a microchannel, and you can see enlarged pictures. I always like these a lot. You cannot really see these by just your bare eyes, but then if you look at a microscope, you can see the world at a reasonable scale, where we take benefit of the special dynamics and properties that materials have at small scale. In particular, this is about combinations of techniques where we do imaging, and also with these microchannels can either put tiny droplets at a predetermined location, or in the inverse, harvest small droplets maybe from cells. So by doing so, we can investigate individual cells, again to support biomedical research. This is an example of a microprosthesis for the inner ear. One of the bones of the hearing system of the human is replaced here by a small compliant mechanism, several millimeters long, in collaboration with physicians in order to alleviate hearing deficiencies. On the bottom row, you can see the working principle where a clamping system is designed, which can be preloaded by this structure here at the bottom. From the Opto-Mechatronics domain, here you can see a couple of examples. This is about satellite communication. There is more and more communication through satellites and also between satellites. Satellites have a tendency of becoming smaller, and by using multiple satellites for one purpose, you can actually increase the performance, but it is required that they can also communicate between them. Apart from electromechanical radiation, light is used more and more. So that results in communication due to laser light. That has great promise, but it also requires very accurate aiming mechanisms and receiving mechanisms. This is work that was done in the ASML machine and partly also at the company. In particular, Opto-Mechatronics systems for adaptive mirror positioning were developed by students. And it's amazing to see that after 1 year of your first year master curriculum, you are able, and that is true for all these projects, to dive into the state of the art, identify research gaps, and develop something that did not exist yet in the world. Very often we can see that our students are able to create a publication based on their thesis work, which shows that they actually contributed to science even during their study. Well, we could continue, but intentionally we left a blank slide here because we like to open the floor for questions. We saw already quite a few come in. I was not able to keep track, but luckily we have Mila from the Taylor Student Association and Evelien from our own department to help you forward those questions to us, and we'll do our best to answer them.
Okay. Good evening, everyone. Just I have a nice question for you. What is the difference between the robotics master, the new robotics master, and our track? Could you specify the difference and maybe also state when you want to choose the one or the other?
Yeah, thanks. That's a great question. First of all, we collaborate a lot with people from many departments, also with the robotics group. But if I were to characterize the differences, is that we are a bit more hardware oriented, whereas the robotics department is more software and control oriented, image recognition, learning control, and those kind of things. So they do quite a bit of artificial intelligence, which does not mean that we don't do it. We also have projects that are related to artificial intelligence, for instance, in synthesis of mechanisms, but also in control of precise motion. But that would be more or less, I guess, the differences.
I have another question. Does high-tech engineering deal with only small-scale instruments and equipment, since miniaturization is mentioned in the presentation?
Yeah, another great question. So what we do is develop technology that is scalable. And there is a clear trend in many machines towards smaller scale. For obvious reasons, small machines use less material, less energy, and interestingly, they also perform better because they have less mass and therefore less inertia, for instance. So it's a very logical trend that precision machines are scaling down. It does not mean that we only work on small machines. We showed a couple of examples where we worked on large machines, like bearing systems based on very tiny air layers or ferrofluids, for instance. And there's other systems that are large, but where the working principle, where the bottleneck, so to speak, is in the precision features. That is where we find our specialty, and that is also much of our research directed to those bottlenecks. And if we overcome them, then we help that technology further. So in summary, we do a lot in general technology that is very often scalable towards the small scale, but we also find applications in larger scale.
I think we then also have a nice question that kind of comes along with this one. What would be the main differences between the multi-machine engineering, mechanical engineering track and our high-tech engineering track?
Yeah, okay, that's also an excellent question. I think the similarity is that much of what those two directions do is system oriented. In both cases, the whole system is considered, and implications from that system view on the particular modules or elements of the system are studied. The difference would be that multi-machine systems considers large structures like a harbor, for instance, with logistics and cranes and bulk material flows and those kind of things. Whereas we are focusing more on machines, and we try to do the same, but then let's say integrate the behavior of the mechanical part, the mechanism, with the actuation system and the sensors and the control into one coherent machine performance. And as I mentioned, more and more we also try to physically integrate the embodiment of the machine to a compact unit.
I have another question. Specifically for students who have done a bridging program, for example, from the industrial EO faculty, industrial design faculty, but maybe also consider students that are coming from the HBO, higher education, or maybe other faculties within our university or other universities. Maybe this is a nice question for you, Ron.
Sure, what is the question?
Well, if you have completed a bridging program to our master from another faculty or from the HBO, is it doable? Will you be able to keep up?
Of course. The bridging program is intended to bridge that gap. So if there is a difference between your previous education and the bachelor program that our mechanical engineering students would have seen, then that difference is solved in that bridging program. So yes, we do have many students coming in from different backgrounds, and they perform excellent. We've got PhD students from various backgrounds, not only mechanical engineering students. So they perform really nicely, and they are a nice contribution to our community.
Yes, and as a matter of fact, those people show a very clear dedication, and therefore they tend to be very motivated and are oftentimes amongst our better students.
Thank you. I have another question. That's what I'm here for, right?
Sure.
How hands-on is our master? Really broad question.
I think Ron can answer that question for the curriculum. I will then answer that question for the graduation projects.
Sure. So within the curriculum, within the courses, we do have a significant amount of theory. Of course, there is some science involved here. However, it needs to be practiced. It needs to be connected to experiences in the lab and also in projects at companies. So we have I would say, a very nice balance between theory and projects and experiments. Not only in the micro nano courses, but also in the design courses. And perhaps before Just starts with his second year, we can comment on the precision mechanism design course, which has a really nice hands-on part to develop the techniques and the knowledge that you learned in the theory part.
Yeah, thanks, Ron. Ron is referring to the course Precision Mechanism Design, where the first quarter is dealing with theory of precision mechanisms, design methods, design principles, and spatial kinematics theory. And in the second quarter of that course, the second half, we apply it to a project problem that is proposed by a company. Every year we have another company. They present us with a design challenge. They want to build a machine, typically, let's say a hypothetical machine, which has several aspects to it. Maybe a mechanical part and a control part or something like that. And then we have teams of 20 students that are subdivided in groups of 5. Each of those groups take one of these aspects, and as a team they have to create a system out of those aspects, or out of those modules. In the end, we present it back to the company. If COVID allows, we actually visit the company. That will not be this year, but hopefully as of next year, as we did in the past. Present our solutions, get feedback from real life engineers, and have a company tour. Then on to the second year, the graduation project. We often see a mix of theory and design. Suppose you have a typical design assignment. You want to design a machine. Then we are super proud if your machine works. And that's not easy to get a machine that didn't exist before to work during your graduation project. Yet that will not be enough, because we're not satisfied until you are also able to explain why, of all the possibilities you came up with, particularly this design, which means that you have to be thorough in your concept generation. And the second thing is, you should be able to explain how well it works relative to maybe a theoretical maximum, like Carnot efficiency or something like that. Because then your performance gains a lot in meaning. If you were to do, let's say, a more research-oriented project, then typically you will have to develop your own test setup, because you will be doing something that was not done before. So you need a dedicated test rig. So also in the more research-oriented projects, there will be design involved. So very often it's a mix of the two.
Thank you, Just. Next question. What industries does this master have application in? And also in extension to this, where do students end up?
Yeah, that's a great question. We cannot anticipate where students end up. Recently, I had students who did a fantastic technical assignment, ending up in banking industry. We also have precision engineers who end up in dredging companies. And so, yeah, people end up pretty much anywhere. I think that is partly thanks to the broadness of our curriculum, and also by the way we design our graduation projects. As Ron already mentioned, we tend to underdefine the graduation assignments, meaning that we have a rough idea on what we have in mind, but the student will dive into the literature, get the latest results, identify a research gap, and is able to tune that. If you want to do more of design, you can choose to do so. If you want to do a little bit more of simulation or modeling, that is also usually possible. Right, so you basically shape your project based on the state of the art and advice from your supervisor, and then produce something that was not done before.
Thank you. I have another good question. What is the percentage of students who have the chance to be admitted to a PhD position, for example, in our own department?
We have roughly 50% students from our own labs or university and 50% from outside, I would say, very roughly. To be honest, I advise students who graduate with us, if they want to do a PhD, to also look around in the world and maybe do a project at another lab to gain more international experience. Because that is important, certainly if you have ambitions for an academic career. But then again, there may be reasons why people prefer to do a PhD at Delft. I would say there are actually good reasons to do that. We always make sure that we have a project ready and guaranteed before we hire people. So it's not like in other countries where you kind of move on into a PhD program. No, we as academic staff, we apply for funding, and only after we guaranteed the funding, we open the position and people can apply.
Okay, thank you. I also have a question about double masters. A few of them, and would it be possible to do a double master with with this master high-tech engineering, and which ones would be the most suitable to combine it with?
That's a question for me or for Evelien?
I can try to answer it. Yeah, so double degree is mostly done with systems and control or biomedical engineering, and I think also the new robotics master could be a nice combination. Sometimes also students decide to combine it with a master of civil engineering, or it could maybe also be combined with aerospace. But I think the most important part is to see or to realize that, of course, this will take a bit longer. You will take the course load of the first year from one master, then you continue on with doing the first year of the other master, and then you combine your knowledge, which you have gained, into this into one master thesis project. So you combine the knowledge of both, and you will find a supervisor of both masters and find a nice project to work in. And then ideally, of course, you will be finished after 3 years, but I think it would be wise to give yourself some space for all the course load and think about 3.5 years, for example. I think we have about 2-3 students doing it average a year. So not many students, but those who do it, they complete it and they think it's doable.
And then maybe tagging into this one as well, is there also a part-time option for this master's, and how long would that typically take? I think this is also for you, Evelien.
Yeah, it's quite difficult to do our master part-time, especially since, of course, in the first semester you will focus on obligatory courses of mechanical engineering and obligatory courses of our own track, and you will continue in the second semester building on this knowledge in choosing electives. Sometimes, if there are specific circumstances where this is needed, we can look for a tailor-made program, in the sense that maybe you focus first on all obligatory courses and then later maybe focus more on your electives. Maybe doing it in 1.5 years, for example, and spread the workload a bit. But it's not only visiting the lectures, it's also preparing for those lectures and preparing for exams. So I think it's quite difficult to combine with a part-time job. Maybe a small part-time job like many students do on the side a bit, but 20 hours a week, I think it's a bit much. But Ron, if you don't agree, let me know.
Largely, I do agree, although I do have examples of students who worked at a company and combined that with a study and are still working with that company, but now full time. So it is possible. I wouldn't recommend it. Of course, it will lengthen your studies significantly. But if you're willing to do that, then okay.
There are questions on how many students enter into this master's, and it is maybe interesting to get a feel on what type of group you will join. We recently saw a rise in numbers. We used to have like 50 students, and in the last couple of years we doubled approximately. So we have an intake of 100 students or so per year in our tracks. As Ron mentioned already, luckily we also have a Taylor Student Association who is very active. They organize many different things, as evidenced by Mila, who is now helping you out with all the questions. But they also do social events and group building activities.
Due to the time, we almost need to wrap up, but I have still some questions. Which software programs are being used in this track, and do you need to download this on your own computer? Ron, I think that's a nice question for you.
Sure. We use different types of software throughout the courses. And yes, most of these packages you will be running on your own laptop or on your own computer. So MATLAB, Console, we have a large list of software that can be downloaded from our central system from Brightspace, where students can download the software they need for the different courses. And but yes, you do need a private personal computer to run this software. Of course, we have computers in the faculty, but at the moment, reaching those computers is more difficult because of COVID, of course. So,
yeah, but we do have the software licenses, so you can download it.
Yeah. And perhaps in addition, it's not only the use of the software, it's also the question how much programming is involved. Well, so that depends largely on the focus area and the topics that you're interested in. So some of us are really programming finite element software packages from the ground up, and some are using complex packages as they are provided by a supplier and using them, understanding them in detail, but not programming in a classical sense. So both the whole range of possibilities is there.
I think we still have many questions, but we need to wrap up due to the time. There will be, like Ron already showed on the slides, also an opportunity to ask questions via Leegwater. Leegwater has an event on the 29th of March. There will be a chat with students, with current master students. Also our own master students will join this session as well. So you can have the opportunity to ask their experience of the master, and also have some general questions. Also feel free to send an email to me. You can find my email address on the website if you look up our master, and then yeah, I will try to answer them as soon as possible. Maybe one interesting last question to answer just before we wrap up is how Opto-Mechatronics is at the moment involved in our master, because there's some confusion about the difference between optomechatronics and high-tech engineering, and at the moment it's integrated.
Yeah, that's a great question. Officially there are separate tracks, but we have integrated them as a focus area of our high-tech engineering. The reason is that the track is still young and growing. And in order for the students to have a larger community, we decided to integrate them for now into the, let's say, daily activities of the high-tech engineering program. So it is officially a track, and we treat it as a focus area in our curriculum.
So I think, unfortunately, we need to wrap up. And thank everybody for their attention and for joining our session.
Yes, thank you so much for your attention and all your questions. We might close this session by showing the info slide with the contact details from Ron and Evelyn. Okay, once again, thanks everybody for your interest, and hope to see you soon.